Alice and Bob are two quantum physicists. They are working on quantum information and quantum computing. Alice is impressed by Bob's intelligence and has fallen in love with him. She thinks about him day and night and wants to tell him her feelings. So how should Alice propose Bob? A romantic date on a beach under a setting sun? Nah, she thinks this is boring. She wants to propose him in a quantum way, using quantum teleportation, and Alice has a plan. Like all quantum physicists share an entangled electron among them, so Alice and Bob also share an entangled pair of electrons. Alice plans to create another electron in a quantum state psi, in which she encrypts her proposal. She then interacts the psi state electron with her half of entangled pair. She then measures the two electrons in her possession, obtaining one of four possible results. She then sends the obtained result to Bob via email. Depending on Alice's message, Bob performs one of four operations on his half of entangled pair. By doing so, he can recover the original quantum state psi. In short, Alice teleported the quantum state psi to Bob, which carries her secret message. This symbol is read as ket psi, and it is basically a column vector. This column vector represents the quantum state of the particle. In our case, we are considering the spin states of an electron, and there are two spin states of an electron. The spin up state, which is denoted as ket0, and the spin down state, which is denoted as ket1. When we write ket psi as a sum of states, example, say ket psi equals 1 by root 2 ket0 plus 1 by root 2 ket1. This implies that this state psi is in a quantum superposition. What it means is that when we measure the state of an electron, then there is a 50% chance that the electron is in state ket0 and 50% chance that the electron is in state ket1. For a general state, say ket psi equals alpha into ket0 plus beta into ket1. The probability of finding electron in state ket0 is mod alpha square, and in state ket1 is mod beta square. If we want to describe quantum state of many particles, we use the operation called tensor product. So if we have two electrons, both in state ket0, then this combined state is represented as ket0 tensor product ket0, which is equal to ket00. And if the first electron is in state ket1 and the second electron is in state ket0, this combined state is represented as ket1 tensor product ket0, which is equal to ket10. Further, if the first electron is in state ketx1, which is equal to A into ket0 plus B into ket1, and the second electron is in state ketx2, which is equal to C into ket0 plus D into ket1. This combined state is represented as ketx1 into tensor product of ketx2, which is equal to AC into ket00 plus AD into ket01 plus BC into ket10 plus BD into ket11. We say that the two electrons are entangled when the combined states of these electrons cannot be written as a tensor product of single particle states. So if beta is an entangled state, then ket beta is not equal to ket x into ket y, where ket x and ket y are single particle states. An example of an entangled state is ket beta 00, which is equal to 1 by root 2 ket00 plus 1 by root 2 ket11. A very interesting thing happens when pair of electrons are entangled. Suppose pair of electrons are in state ket beta 00, and if we measure the first electron and found it in state say ket0, then the other electron is also found in the state ket0. It doesn't matter how far apart the two entangled particles are. Measuring one fixes the outcome of the other. Just like your computer's electronic circuit is built using logic gates, we also have quantum gates, which manipulates the state of your electrons. Example is an X gate, which if acted on ket 0 gives ket 1, and if acted on ket 1 gives ket 0. That is, it flips ket 0 into ket 1 and vice versa. There are another two gates, the Z gate and the H gate. The Z gate, which leaves ket 0 unchanged and flips the sign of ket 1 to minus of ket 1. H gate acts on ket 0 to give 1 by root 2 ket 0 plus ket 1, and acts on ket 1 to give 1 over root 2 ket 0 minus ket 1. These gates acts on single particle states. We also have gates which acts on two particle states. An example of this is an C0 gate. Its action is, if the first particle is in state ket 0, then the second particle state is unchanged. And if the first particle state is in state ket 1, then the second particle state is flipped. To start off, Alice has an electron and Bob also has an electron. These two electrons are in entangled state ket beta 00. Alice takes another electron and changes its state to ket psi, which is equal to alpha ket 0 plus beta ket 1, where her secret message is encrypted in numbers alpha and beta. Now Alice has two electrons and Bob has one electron. The total quantum state of these three electrons is written as ket psi 0, which is equal to ket psi, which is the Alice's psi electron, and a tensor product it with ket beta 00, which is the state of two entangled electrons of Alice and Bob. So ket psi 0 is equal to 1 by root 2 alpha into ket 00, 0 plus alpha into ket 01, 1 plus beta into ket 10, 0 plus beta into ket 11, 1, where comma separates the two electrons of Alice and Bob. Then Alice sends her two qubits through a C0 gate, which gives the state ket psi 1. Alice then sends her first qubit through the H gate to get the state ket psi 2. After evaluating, we get four terms for ket psi 2 as this. The first term has Alice's qubit in state ket 00 and Bob's qubit in state alpha into ket 0 plus beta into ket 1, which is the original state ket psi. Therefore, if Alice performs a measurement and obtains the result as ket 00, then Bob's system will be in the state ket psi. Similarly, if Alice gets the measured state as ket 01, then Bob's state will be alpha into ket 1 plus beta into ket 0. Similarly for other two states. Thus, depending on Alice's measurement outcome, Bob's qubit will end up in one of these four possible states. To know which state it is in, Bob needs to know about Alice's measurement results. So Alice writes a letter to Bob telling the result of her measurement. Once Bob gets to know her outcome, Bob can fix up his state, recovering the original state ket psi. For example, if Alice's measurement yields ket 00, then Bob doesn't need to do anything. Bob's state is already in ket psi. If her outcome is ket 01, Bob can fix up his state by applying X gate. If the outcome is ket 10, Bob can fix up by applying the Z gate. And if the outcome is ket 11, Bob can fix up by first applying the X gate and then applying the Z gate. So finally, Bob has the state ket psi prepared by Alice. They have successfully teleported the quantum state psi. After that, Bob measures his state, and then they repeat the teleportation procedure many times with the same state psi. By doing this, Bob finds that mod alpha square is equal to 1 by 4 and mod beta square is equal to 3 by 4. He gets the code, decrypts it, and finds that Alice has actually proposed him, and that also using quantum teleportation. Will he say yes or will he say no? What do you think? Write your opinion in your comments and never